Hey everybody. So what we've covered so far is we've talked about what is an equilibrium, and then we've looked at equilibrium expressions and calculating equilibrium constants using those expressions. Now, in those expressions, I talked about how you could be asked to calculate the equilibrium constant given all the equilibrium concentrations for that expression, or you could be asked to calculate one of the equilibrium concentrations if you're given the equilibrium constant. And so those are some simple algebra formulas that you can just use to calculate those things and find those answers. For this, though, we have situations where sometimes we end up with a question that will give us an equilibrium concentration, but then also give us another concentration that's not an equilibrium concentration. And if you remember from the previous videos, I said that when you're using equilibrium expressions, only the equilibrium concentrations can go in those expressions. So if you have a question like this, where this question here is asking you to calculate the equilibrium constant, but you don't have all the equilibrium concentrations, then there's a process in which you have to use in order to figure out what all of the missing equilibrium concentrations are, so that you can then plug that into your expression and find what the question's asking for. And so this is this concept of ICE tables. So if you take a look at this problem here, what we've got is this balanced chemical equation, and it says that we're putting 2 moles of this N2O4 gas, this dinitrogen tetraoxide gas, into a container that's 4 liters in volume. And it gives us the equilibrium concentration of NO2 gas, and it tells us that it's 0.24 moles per liter. So here's the information that we've got here in the question, in terms of this number and then this number here. Now, if you take a look, sometimes they'll write questions like this, and all they're really getting you to do is to understand that when I have 2 moles in 4 liters, what is the concentration of that substance? So the concentration of this substance is 2 moles per 4 liters, which is 0.5 moles per liter. It's just 2 moles divided by 4 liters to give you your moles per liter unit, and you get 0.5 moles per liter. And so what this number is this is the concentration of the N2O4. And you can see that it's been put or placed into a container. And so when I place it into the container, remember equilibriums are established when systems are closed. So I put it into the container, I've got to close it up. At that point, the reaction can start to go. But at time 0, N2O4 hasn't begun the reaction yet. So if I'm talking about like initial concentrations of the substances in this equilibrium reaction, I know that my initial concentration of N2O4 is 2 moles in 4 liters, which is 0.5 moles per liter. Now sometimes these tables that I'm going to show you how to do get a little congested. And so one shorthand that we can use for units of moles per liter is we can use what's called molar, which is just a capital M. So from here on out, you'll probably see me writing concentrations like that. And what that means is 0.5 moles per liter. If you need to write that down, you can. Now initially in the container, remember we placed N2O4 in the container. There isn't any NO2 in the container yet because the reaction hasn't begun initially at time 0. But probably quite soon after I place that stuff in the container, I am going to start to have some NO2. And so N2O4 is going to change into NO2. So what is that change? Well, we know that reactions always react based on ratios. So I know that one of these is going to make 2 of these. So one N2O4 is going to make 2 NO2s. That's what the reaction tells me. And so I know that I have some of this and I have none of this. So the amounts of this are obviously going to go down because I'm going to use this to make this. And because I have none of this to start, the amounts of this are going to go up. And so the change here is going to be a negative amount to represent that I'm losing a certain amount of concentration of N2O4 as this reaction progresses. And over here, the change is going to be positive because obviously initially the reaction is going to run towards the products faster than it is in the other direction. So I'm going to have a net change here of a positive amount because the concentration is going to go up initially. And so by how much? Well, that's what these coefficients are for. This is a coefficient of 1, this is a coefficient of 2. So by whatever change that is going to be, I can denote that number, that unknown number, by the letter x. It's an unknown number, I don't know what it is. And this is going to change by a negative 1x because one of these makes 2 of these. And so this is going to change by twice as much. For every one of these that I lose, I'm going to gain 2 of these molecules. And so this would be positive 2x. And so that's what the change represents. Now finally, once the change is complete and the rates of the forward and reverse reactions are now equal, then I will have established equilibrium and I will have equilibrium concentrations. So I know at that point, once that change is done, I'm at equilibrium. Now, this equilibrium concentration here is given to us. It's 0.24 moles per liter. Now remember, I can write this just as 0.24 m. For this one here, well, before I get to this one, let's finish off this one. So I had none, I gained a 2x, whatever change that was, and I ended up at 0.24 moles per liter. So I can create a mathematical equation out of this. It's quite simple, which is just simply 0 plus 2x equals 0.24. And so if I do the algebra here really quick, and I'm not going to go through the inner workings of algebra in this video, but x is going to be equal to 0.12. And that is the change for x, which is 0.12 moles per liter. So if I know what x is, then I can plug x into this side of the formula as well, which would then help me calculate what the equilibrium concentration is for N2O4 based on this information. And so I know that 0.5 minus 1x is going to give me my equilibrium concentration. Well, if x is 0.12, I can just go 0.5 minus x, which is 0.12, is going to give me 0.38 moles per liter. I'm not going to write that anywhere on the page. Doesn't really matter where you show that work, but it's a good idea to show it somewhere. So you could do something like that, and that might be a little bit overkill, but just to kind of illustrate how that whole works. Okay, so 0.38 is my equilibrium concentration for N2O4. And you can see using this chart and this table of what we call ICE tables helps me identify equilibrium concentrations for substances that I'm not given in the question. And so the reason we call these ICE tables is because we are dealing with an initial, a change for the reaction, and then what finally the equilibrium concentrations are for that reaction. And that's why we call these ICE tables. So oftentimes you'll see me just write out when we do practice questions for these ICE like that. And you need to know what the I and the C and the E stands for so that you can properly set these tables up and do these questions. Now at this point, the question says find the Kc value. So now that I have my equilibrium concentrations for both of those substances, I can find what the Kc value is. To find the Kc value, I need to write a proper Kc expression. And so my Kc expression is going to be the concentration of my products over the concentration of my reactants. And in this case, it's pretty simple because I just have one reactant, one product. Notice that this concentration of NO2 must be squared because it has a coefficient of 2. And notice that both of these have a state of matter of gas, so they can both be inserted into the expression. So then I just plug the numbers in and do my calculation. So 0.24 moles per liter squared divided by 0.38 moles per liter, and I plug that into my calculator. and you should get 0.15 for your Kc value. And that's how you do ice tables. If you'll notice what the Kc value is, it's less than 1. If you want to go back into your notes or check a previous video, it would be good for you to remember what a Kc value of less than 1 means. And if you cross-check that with your equilibrium concentrations, that should make sense. So I'll let you check that on your own, and we'll move on to the next concept. Thanks guys for watching.